Yo, it's the 2019 A2 Unit 4 Mechanics questions. It's question 9. This is the moments question. This freaked everybody out because it was completely different to anything we'd seen before. But I love this question. And when you go through it, it's actually not that difficult. It's just a stack of algebra that's completely doable. So the diagram looks horrific. We've got inequalities because these lights can move on tracks, right? And there's hardly any numbers involved at all. They don't want any sort of numerical answer. They want an expression for the tension in wire 1 that looks like that. And they then want a similar expression for the tension in wire 2, right? All you've got to do is take a deep breath and draw the diagram like you would in class, like it was normal weights. Put in the information, take moments from the one wire, do all the algebra, take moments from the other wire, do all the algebra, and it comes out, right? So let's go through it. So, hoping this is still on camera. There's a simplified version of the diagram, right? The three lights all have the same weight, mg. Excuse me. They've told us there's a distance of 1 meter between the two wires. The actual track itself is 1.8 and it's symmetrical, so it's 0.4 each side if that's needed. I know that this light can move a distance of A from the wire, this light can move a distance of B, and this light can move a distance of C, right? So let's just, to get the expressions for T1 and T2, let's take moments, first of all, from T2, right? So I'm going to take moments from this point here. So let's look at what would try and spin that system clockwise, first of all. So T1 is trying to spin it clockwise. And this weight here is also trying to spin it clockwise, and this is a distance C from T2, right? So the total trying to spin it clockwise is T1 plus mgc, and that'll be equal to these two that are trying to spin it anti-clockwise. The reason it's equal, of course, is because it's in equilibrium, it's not spinning. So this weight here, the distance of this from here to where I'm taking moments from T2 is the 1 meter minus this B, right? So this is 1 minus B mg. And then similarly, this weight here has a distance of 1 plus this A. So that's 1 plus A mg. So there's my expression from taking moments about T2. Now I just got to tidy it up and make it look like the answer they gave me on the sheet, right? So let's do that. Let's just keep T1 on its own on the left, take that over, it becomes minus mgc, okay? Multiply out these brackets, I got a plus mg there, a minus bmg there. Now that's a long-winded way of doing it, right? So I'm hoping you could spot straight away, hang on, all three terms have got mg. So let's just bring the mg out, factorize it, and then tidy up what's left. So if I bring the mg outside, I've obviously got times by minus c for that one, times by 1 minus b for that one, times by 1 plus a for that one. If I tidy this bit up, 1 plus 1 is 2, then the plus a, then the minus b, then the minus c. And hey presto, that was the answer they wanted us to show on the exam question. It then says find a similar expression for T2, so just do exactly the same thing again. Take moments this time from T1. Okay, so let's have a look. What's going to try and spin it anti-clockwise? First of all, is the way I've done it. So I've got T2 trying to spin the system anti-clockwise, and I've got this one, MGA, trying to spin it anti-clockwise. The other two are trying to spin it clockwise, which is MGB, and this one, MG, is a distance of the 1 meter plus the C away. Do exactly the same process as we've just did. Take that over. It becomes a minus MGA. Just leave T2 on its own. Bring the MG outside and factorize. So I've got, there's a 1 there, there's a plus B there, there's a plus C there, and there's a minus A there. So there's my expression for T2. Okay? So it really wasn't that difficult. It looks horrific, but it wasn't, especially if you've set up your diagram correctly and taken out all the guff that was in the original diagram. Then it says find the maximum possible value of T1. Now this takes a bit of thinking, right? To get the maximum possible value of T1, you are going to need the absolute minimum value of moment at T2. So you've got to think, where would these lights be positioned for that to happen? Now, of course, I can bring light C right underneath T2, so it has no moment at all. And then if I push these two as far away from wire 2 as possible, that will give me the maximum tension being created under wire 1. So I'm going to put C right underneath wire 2, so that'll have a distance of 0. I'm going to bring B right across as far left as possible, so that would give me a value of dB as being 0.1. And I'm going to take A as far left as possible as well, and that would give me a value of dA of being 0.3. Now what I do then, look, is I put those values that I just explained into the original T1 formula. 2.3, take away 0.1 is 2.T, leave it in terms of mg. So the maximum tension in T1 would be 2.2 mg. And then finally it says, without carrying out any further calculations, and that is in bold, so it means this is pretty simple really, just think about it. Write down the maximum possible value of T2. Well, it's going to be exactly the same as T1 for this to remain in equilibrium and suspended horizontally. If T1 was at max, then T2 would have to be the same as well at max. So T2 must be the same to keep it suspended horizontally. What a brilliant question, said no one ever. Enjoy.